power equal to 14 100-watt light bulbs put together. Every day, after dark, we switch on and off different light sources dozens of times. To us, these are mechanical actions we don't even need to think of. But what if we fall asleep at home with the lights on and wake up in the distant past? It sounds unbelievable. And what does light have to do with it, you may ask? In the fall of 2022, two independent groups of scientists, physicists from Oxford and Vienna, sent a light particle into the past. Later, they published the research results on arXiv. Having split a photon with a special crystal, they achieved what they called quantum time reversal. The photon, in the process, moved into the future and the past simultaneously. This research may not allow humans to move back in time, but it can finally explain the mechanism of such travel. And it all can be possible thanks to ordinary light. But you don't even suspect what other superpowers light has. Sunbeams are the only source of energy and life on Earth, but the first light appeared long before the sun was born. Our universe emerged almost 14 billion years ago. Immediately after the Big Bang, it was plasma of such density and hotness that nothing could penetrate it, including light. It took the universe almost 400 million years to expand and cool down enough that electron and proton interaction resulted in the formation of hydrogen, and the first light appeared. Soon afterward, the universe passed the rapid expansion period and increased the first light's wavelength, turning it into microwaves. They make up the cosmic background radiation we call relic radiation. It's amazing that at any moment, through a telescope, we can see the light that was born billions of years ago at the same time as the universe. Why doesn't relic radiation vanish? What is it made of? People first thought about the nature of light well before Christ. The ancient Greeks were positive that we see the surrounding world because our eyes radiate vision beams which touch objects. Only in 1672, an English physicist, Isaac Newton, in his new theory of light and colors, stated that light comprises different colors of different refractivity, and it's not pure white as Aristotle claimed. Newton proved it experimentally. He directed a sunbeam at a prism and saw 7 rainbow colors on the screen behind it. Then why do we perceive light as white? The thing is that the human eye is a lot less sensitive to sunlight. That's why we can't see the whole spectrum. Newton also thought that light consisted of material particles, which he called corpuscles, and they moved in a direct line from the light source. His theory could explain how light spreads and reflects, but not how it refracts. Almost 20 years later, a Dutch physicist, Christian Huygens, published a work in which he proposed a theory of light as a wave. And only a century later, an English physicist, Thomas Young, supported him. In his famous experiment, he proved that light spreads as a wave. The scholar consecutively passed it through 2 barriers. The first one contained 1 slit, while the other had 2. If light consisted of particles, 2 lines would emerge on the screen behind the second barrier, 1 in front of each slit. However, what emerged on the screen was an interference pattern. Due to the fact that the waves overlapped, there was an increase in their power in some parts and a decrease in others. That's why behind the second barrier, instead of the 2 light lines, we see a series of darkened light stripes resembling a barcode. The concept of light's wave-like nature dominated up until the 20th century, until Albert Einstein discovered that light actually consists of weightless subatomic particles. The scientist referred to them as light quanta. Today, we know them as photons, and that each combines qualities of both a particle, impulse and energy, and a wave, frequency and length. This very duality constitutes light's first superpower. It enables the photon to cover gigantic distances in split seconds as a wave and physically interact with the surrounding world as a particle. For instance, it can knock electrons from atoms and thereby charge solar batteries or participate in photosynthesis. But what other superpowers is the photon hiding from us? Light is electromagnetic radiation perceived by the human eye. Born in the sun's core, hydrogen atoms bump against one another, triggering powerful energy bursts, the light from which can kill us because this is gamma radiation, the strongest radiation in the universe. These rays' intensity is millions of times higher than visible light. However, they can't leave the sun at this moment. As a rule, having left the core, the newborn photon requires at least 100 years to pass through the thick layer of hydrogen atoms. It loses a fraction of its energy in the radiant transfer zone. There, the photons bump against charged particles of plasma, which pushes it to the surface, but it reaches it as an X-ray. On average, photons spend there around 170,000 years, though some can stay for millions of years. Then, the photon goes to the convective zone, stretching for 200,000 kilometers. Hitting plasma atoms, the photons heat them to a boiling point. But the atoms simply absorb the photons and push them to the surface. This path takes about a week. During this time, the photons cool down enough to become visible light, and only after all of these, they're ready to leave the sun's surface. An individual photon escapes the photosphere and ends up in space, where it can live for billions of years. That is, it's virtually immortal. And this is another of its superpowers. But those photons that travel towards Earth have a different fate. They have 8 minutes to reach our planet and die. A photon that enters a building will fly around it, bumping off its surfaces. When it completely loses its energy, one of the objects inside will absorb it completely. Thanks to this process, things become warm in the sun, as according to the first law of thermodynamics, energy can't be created or destroyed. It simply converts from one process into another. When we switch on the light in the room, trillions of photons fill it, most of which are absorbed by the objects, but a fraction of them is reflected from surfaces. This is what enables us to see things around us. While the lamp is on, the room receives a constant photon flux. All these processes, from the lamp's radiating photons to their reflection and absorption, takes place in roughly 1/1,000,000th of a second. However, not only the usual light sources radiate photons, but also humans. The ability to glow some living organisms have is called bioluminescence. In 2009, Japanese scientists decided to find out if humans also possess this superpower. Their experiment was published in the PLOS ONE journal. The researchers put volunteers in a dark room with highly sensitive cameras. There, they registered luminescence and found that its brightness wasn't constant. People glow the dimmest at 10 in the morning and the brightest at 4 in the afternoon. The scientists related to the body's metabolism. However, they didn't reveal any correlation between luminescence and body heat. Our glowing is absolutely cold. At the same time, our faces glow a little brighter than other body parts. Nonetheless, the scientists haven't found which particular biochemical processes are responsible for the effect. The intensity of our luminescence is about 1,000 times lower than the human eye can detect. It's not designed to perceive light waves ranging beyond 400 to 800 terahertz. That's why humans can't see infrared and ultraviolet rays, which significantly exceed these limits. As such, the bigger share of the spectrum remains invisible to humans, while having a huge impact on all life on Earth. This is yet another of light's superpowers. But could we possibly control the superpowers the photons have? Probably yes, but how can we catch them? The thing is that the photon is a particle of no mass. This is the superpower that makes it travel incredibly fast. The speed of light traveling in a vacuum is around 300,000 kilometers per second. Light can circle Earth in less than 1/7 of a second. According to Albert Einstein's special relativity theory, nothing can move faster. At the same time, when a photon is moving, time for it stops. What if we can harness this superpower and use light speed for space flights? If someone could move at the same speed as a photon, time for them would move slower than for observers from Earth. And at such speed, the universe would look different. The stars the person approaches would be blue, and those staying behind them would be red. The explanation for this is that light waves of the stars in front of them would shorten, making the objects look blue, while the waves from those behind would extend to become red, triggering an extreme Doppler effect. But astronauts would barely have time to enjoy the view from the porthole, as what under other circumstances would be a handful of indistinguishable hydrogen atoms at such great speed turns into a host of dangerous particles. Colliding with the spaceship, they'd heat it to incredible temperatures very fast. Theoretically, shields and sheathing made of a special material which would prevent the spacecraft together with the humans in it from roasting could solve the problem. But regardless of all the risks, in 2020, Harvard researchers announced a way to help approach light speed on interstellar ships. They suggest using a supernova blast. To catch its energy, you'll need a solar or magnetic sail to help create pressure and propulsion that requires no fuel. The spacecraft rigged with the sail, weighing less than half a gram per square meter, must be placed 1,000,000 kilometers from the supernova. The sail has to be made from a folding, highly reflective material. However, in this way, we'd only reach 1/10 of light speed. But even photons themselves don't always move at maximum speed. Unless in a vacuum, they can slow down as they pass through some materials. The extent to which a certain environment slows light is its index of refraction. For example, in Earth's atmosphere, light moves almost as fast as when traveling through vacuum, only slowing down by 3/10,000ths of light speed. But going through such dense material as diamond, it slows down by almost half. Nevertheless, it still travels through the gem at over 100,000 kilometers per second. So, photons can move slower than light speed. But can they move faster? Given all the physical laws, no. Once light speed is reached, time stops. For the photon too, its whole life is a single moment. In general, making it move faster is the same as trying to make an unmoving car go even slower. But researchers from the Lawrence Livermore National Laboratory in California and the University of Rochester in New York conducted an experiment and proved it's still possible. They're sure that light has certain qualities making it possible to bypass even inviolable rules. The scientists managed to exceed light speed by 30%. They put photons into hot plasma where, bumping against one another, their impulses created waves moving at a group speed. Using a laser, the researchers ripped electrons out of hydrogen and helium ion fluxes. Doing so, they altered the group speed of the impulses sent by the second light source. This is yet another of light's paradoxical superpowers, which can even break physical laws. But if the scientists help the photon accelerate, does this mean it can gain superpowers? If earlier scientists only discovered the photon's superpowers, today they can endow it with new ones and use them to achieve their goals to benefit humanity. In 2016, Australian scientists published a report in Nature Physics. The researchers did an impossible thing. They literally froze light. The scientists shone infrared lasers into an ultra-cold atomic cloud. Atoms absorbed a part of the photons, while the other part remained trapped, frozen in the cloud. Thanks to this research, quantum computers can become as readily available as smartphones. But what if we learn to not only stop the photon, but also control its movement? A team of researchers from Darmstadt University managed to stop a photon and hold it still for 60 seconds. They share the results of their work in Physical Review letters. They used a completely opaque crystal. Having cooled it down to an extremely low temperature, they burned it with a laser to trigger quantum superposition of the two states and make it transparent for a particular frequency band. Then, they used another laser to target the already transparent crystal. In the process of radiating, they switched off the crystal's transparency, and the laser's light found itself trapped. Using the same method, the scientists managed to hold a 3-line light image. Imagine you shone a flashlight into a room and then shut the door. And when you open the other door later, the light breaks free. The time spent trapped may vary depending on the crystal type. As for now, the main problem is that it doesn't work at room temperature. The ability to manipulate light's movement is a huge step toward developing quantum routers. Only they can help create the absolutely hacker-proof and ultra-fast quantum internet. But at the same time, scientists continue experimenting with light's other qualities. Researchers from the Utrecht University and Vienna University of Technology claim they created unique light waves that can even travel through opaque materials. They published the results of their study in Nature Photonics. The scientists created light beams that remain virtually unaltered in the opaque surroundings, only slightly weakening. The beam passes through an obstacle and a light pattern appears on the other side, having the same shape as if there were no obstacle at all. As a heterogeneous, light-diffusing environment, the scientists used zinc oxide, an opaque white powder. During the experiment, the scientists transmitted various specific light signals through the powder and studied how they ended up on the sensor placed behind it. Are we really going to be able to even see through walls soon? Such discoveries erase all the boundaries of imagination, and in medicine and biological studies, they'll lead to a true revolution. Hospitals use X-rays to look into the body, as owing to the greater wavelength, they can penetrate our skin. The ability to focus light on particular points inside an object opens absolutely new possibilities. With this approach, we could even look inside cells. Moreover, researchers keep looking for alternative light sources, and they've already learned how to extract it from sound. It's called sonoluminescence. However, currently it only works in liquids. The essence of sonoluminescence is creating tiny bubbles in liquid which implode, collapsing rapidly. When a bubble implodes quickly, it releases energy in the form of heat and light. As a result, the surrounding liquid shines brightly for a brief moment. The temperature in the sonoluminescence process could virtually reach tens of thousands of degrees Celsius, which is hotter than on the sun's surface. This effect was first discovered in the 1930s, but only in the 1980s, researchers began studying it in depth. Ever since, scientists have discovered that sonoluminescence isn't peculiar to water alone, but also to other liquids, including some gases. At the same time, a small amount of energy can produce a rather powerful light beam. With this research, we'll probably forget about traditional light bulbs and illuminate our homes with our favorite music very soon. Thanks to the superpowers of the photons and the scientists studying them, even yesterday's science fiction is becoming today's reality. A Canadian company, Hyperstealth Biotechnology, has developed and patented a thin and flexible material that, as they claim, enables quantum invisibility. The plastic-like quantum stealth consists of microscopic lenses penetrating which light beams scatter. As such, everything situated at a certain distance behind the material becomes invisible. It doesn't bend the beams around the object in the visible spectrum only, but also in the ultraviolet and infrared. This enables making it invisible to eyes, night vision devices, and thermal imagers. If we already know how to turn invisible, moving at light speed and time traveling are just around the corner. What do you think?